There are stars in our universe. That should not exist. Not according to our equations, not according to our models, not according to the limits we thought were unbreakable. And yet, they shine, quietly, stubbornly, almost defiantly, as if the cosmos itself enjoys bending its own rules. Astronomers call them forbidden stars, not because they violate the laws of nature outright, but because they stretch those laws to points where they begin to tremble. One of the most puzzling examples is the existence of stars with masses far above what should be physically stable. There is a theoretical upper limit, something called the Eddington limit. It describes how bright and how massive a star can be before the pressure of its own radiation becomes so strong that it should blow its outer layers away. But in certain young, dense regions, astronomers detect giants that seem to exceed this threshold. They burn so violently, their cores so compressed, their luminosity so intense, that they should collapse or tear themselves apart. And yet, they hold together, at least for a while. Some theories suggest that these stars might not be single objects, but tightly bound clusters masquerading as one. Others propose exotic internal structures, where rotation or magnetic forces redistribute pressure in unusual ways. Whatever the reason, these monsters remain standing, balanced on the edge of what physics allows. Then, at the opposite end of the cosmic spectrum, we encounter the ultra-cold white dwarfs. White dwarfs are the leftover cores of dead stars, objects that normally stay incredibly hot for billions of years. But some appear too cold, colder than our models predict, as if they had far more time to cool than the age of the universe should permit. It's like finding a piece of metal still cold, even though it should have been cooling since the dawn of time. How could a star have cooled past the theoretical limit? Maybe it radiates heat more efficiently than expected. Maybe it has an unusual mix of elements. Or maybe its true age is much greater than we think, hinting at events or cycles we have not fully understood. And then we step even further into the shadowy side of astrophysics, where theory meets speculation. Here reside the dark stars. These hypothetical objects are not made of darkness, but are fueled by something invisible. The annihilation of dark matter in the earliest universe, where gas was pristine and dense. Pockets of dark matter may have accumulated in the same regions where stars were forming. If dark matter particles can annihilate and release energy, then a star containing a dense core of this substance might shine, not because of nuclear fusion, but because of dark matter itself. Such a star would be huge, larger than modern stars, and surprisingly cool on its surface. Soft, swollen, luminous, like a red lantern in primordial darkness. No one has ever confirmed such an object, but telescopes like the James Webb Hound candidates, ancient points of light that appear too large, too bright, and too young to fit our standard models of early star formation. Whether these are dark stars or simply unusually massive early galaxies remains uncertain, but the possibility alone suggests that the universe may contain forms of stellar evolution powered by physics we barely understand. Another kind of forbidden star. Lives not in the early cosmos, but hidden within our own galaxy. These are stars without heavy elements. Stars made only of hydrogen and helium, the original ingredients forged after the Big Bang. In theory, the first generation of stars, the so-called population, 3 stars, were enormous, short-lived, and violent. They should have died billions of years ago, leaving behind no survivors. And yet, astronomers sometimes find stars with astonishingly low metal content, so pure, so chemically primitive, that they seem like relics from a universe that was still young. If even a few of these stars truly survived, it would mean the early cosmos created more diversity than we expected. It would mean that cosmic history is not as straightforward as the textbooks suggest. And then, far from the early universe, we find another class of forbidden objects. The hot Jupiter's gas giants, orbiting so close to their parent star that their atmospheres should be stripped away in just a few million years. Imagine a planet as large as Jupiter swinging around its star every day, or even every few hours, its skies scorched, its clouds boiled off, its outer layers pulled outward by tidal forces so extreme that the planet should unravel. But many of these worlds still exist, still orbit, still cling to their atmospheres, as if held together by some stubborn resilience. Some lose mass constantly, forming long comet-like tails. Some show atmospheres heated beyond what chemistry predicts. Some contain elements that should not survive such intense irradiation, and their very existence forces us to rethink how planetary systems form, how they migrate, how they endure. Across all these examples, a single theme emerges. The universe does not obey our expectations. It obeys itself for every rule we believe we understand. There is an object quietly bending it in some distant corner of space. Reminder that our knowledge is still incomplete, that the cosmos remains untamed, that the map we draw is always smaller than the territory it tries to describe. These forbidden stars, these unlikely worlds, are not errors. They are invitations, signals telling us that reality is larger than our theories allow, and somewhere beyond the limits of what we see. The next impossibility is already shining. But the story of forbidden stars doesn't end with the outliers we already know. The deeper astronomers look, the more they find objects that behave like quiet challenges to the universe's own instruction manual. Some of these stars violate expectations, not through their mass, nor through their temperature, but through the sheer strangeness of the processes inside them. Take the stars, whose internal reactions should not be possible under the classical rules of nuclear fusion. In certain dense environments, fusion may proceed even when temperatures are lower than the thresholds predicted by theory. It's as if the particles inside these stars find shortcuts, tunneling through energy barriers that should be impenetrable. Quantum mechanics permits such tunneling, but the rate at which it occurs should be far too low to matter on astrophysical scales. And yet, some stars shine with precisely this unexplainable efficiency, maintaining luminosities that do not match their calculated fusion output. It's a whisper from the quantum world, echoing through stellar matter, changing the way the cosmos burns. And then there are objects whose rotation defies stability. A star that spins too quickly should tear itself apart, its equator flung outward by centrifugal force. But astronomers have cataloged stars rotating near or beyond the theoretical disruption limit. Their equators bulge, their poles flatten, they glow hotter in some regions and cooler in others. Some even eject material in sudden bursts, rings of gas that drift away like ripples from a stone tossed into water. These stars seem to exist at the boundary between cohesion and collapse, as if held together by a delicate arrangement of gravity, turbulence, and magnetic fields. And in the quiet backdrop of the galaxy, we discover another odd category: stars that wander alone, ejected from their birthplaces, with velocities so extreme that they escape the galaxy entirely. Hypervelocity stars, objects flung outward at millions of kilometers per hour, launched by encounters with supermassive black holes or collapsed binary companions. Some move so fast that their escape trajectories lead them into intergalactic darkness, where they will drift for eternity, with no star field around them, no cluster, no spiral arms, nothing but the faint glow of the cosmic background. While these are not forbidden stars in the strict sense, their survival in isolation, their ability to maintain stability while hurtling through emptiness, makes them feel like outsiders to the usual order of stellar evolution. And still, the cosmos provides deeper puzzles. Consider the possibility of stars made mostly of particles we have never seen, exotic stars, hypothetical forms of matter that could emerge in the densest regions of the universe. quark stars, where protons and neutrons collapse into a sea of free quarks, pre-on stars made of particles even smaller than quarks themselves. If such particles exist, boson stars, compact objects held together, not by ordinary matter, but by scalar fields, smooth, continuous entities that might fill the universe, much like dark matter does. These strange stars have never been confirmed, and perhaps never will be, but their existence does not violate the laws of physics. Instead, they stretch those laws into unexplored territory, filling the theoretical landscape with intriguing possibilities. Observationally, they might mimic neutron stars, or black holes, or appear as dim, compact objects without clear signatures. If just one of them were found, it would expand the periodic table of reality itself, revealing a layer of structure hidden beneath known matter. But the most unsettling category of forbidden stars is not exotic in a physical sense, but in a temporal one. Stars that should have died long ago, but continue to shine. There are ancient subdwarfs, older than the galaxy they live in. Stars whose estimated ages brush dangerously close to the age of the universe itself, or even exceed it within the error margins. These anomalies force astrophysicists to revisit the methods used to calculate stellar ages. Maybe the models are slightly off. Maybe the chemical assumptions are incomplete. Maybe the early universe contained conditions that allowed certain stars to persist far longer than expected. Each possibility carries profound implications, and as our instruments improve, as telescopes gather more light, and observatories stretch their sensitivity to wavelengths once unreachable, we start encountering signals that do not match any known stellar category. Strange periodic dimmings, spectral fingerprints that resemble no existing element. Objects that brighten and fade with rhythms beyond any natural stellar process. Some of these anomalies are explained by dust, or by binary interaction, or by instrumental error, but not all of them. Some remain silent, persistent, waiting for an interpretation. A handful of astronomers have even speculated about engineered stars, objects altered or stabilized by advanced civilizations, while there is no evidence to support this idea. The mere existence of unexplained stellar behavior keeps such possibilities within the wide, distant margins. The imagination, because the universe, in all its quiet vastness, does not owe us simplicity. It offers surprises. It offers puzzles. It offers structures that evolve in ways we have not anticipated. Forbidden stars teach us something fundamental. They reveal that the rules we write are only approximations useful but incomplete, and that hidden beneath the surface of familiar physics, there may be deeper layers, subtler mechanisms, forces, and particles, not yet integrated into the picture. The cosmos is not static. It is not fully mapped. It is not finished, revealing its inventory, and in that incompleteness, that wide frontier of unexplained stellar behavior, lies the essence of discovery, the forbidden stars, the impossible worlds, the unpredicted anomalies. They are not accidents. They are beacons, signals flickering from far-off regions of time and space, reminding us that the universe is far stranger than our equations imagine. And as long as these stars shine, as long as they continue to exist, despite the odds, they whisper a single message into the silence of the cosmos. There is more to learn. There is more to uncover. And the laws we know are only the beginning. The universe, in its quiet vastness, hides motions so extreme, so unexpected, that even the most advanced theories struggle to explain them. Most cosmic bodies follow the predictable choreography of gravity. Stars orbit their galactic centers. Galaxies drift along filaments. Clusters tug on one another across immense distances, but scattered across the cosmos, we find objects that move far faster than they should, faster than the mechanisms of gravity allow, faster than entire models of cosmic structure predict. These bodies do not simply travel. They escape. They pierce through gravitational wells, fly beyond the boundaries of the systems that created them, and continue accelerating long after they should have slowed. Among these outliers, the most dramatic examples are the hypervelocity stars. A hypervelocity star is an object so fast that it breaks free from a galaxy as easily as dust blown from a windowsill. Some travel at more than 1,000 kilometers per second. Some approach 2,000, and a rare few move even faster. To understand how unusual this is, consider that most stars in a galaxy like the Milky Way drift along at only a few hundred kilometers per second, kept gently bound by the galaxy's gravitational field. But hypervelocity stars are launched like bullets, fired from the center of the galaxy after a lethal encounter with the supermassive black hole. When a binary star wanders too close to such a black hole, one star may be captured while the other is ejected at extreme speed. The black hole acts like a slingshot, hurling the surviving star outward and away forever. These stars travel so far and so freely that they eventually leave the entire Milky Way behind. They enter intergalactic space, a place without constellations, without neighboring suns, without even the gentle glow of a spiral arm. And yet, even these extreme speeds are simple Compared to another mystery, in 2017, an object entered the solar system from interstellar space, a slender, elongated body, faint, fast, silent, and unlike anything seen before. It was named Oumuamua. Its trajectory was hyperbolic, its speed enormous, its origin undeniably alien to our solar neighborhood. But the true mystery appeared only after it passed the sun. It accelerated, not from gravity, not from jets of gas, like a comet would produce. The object sped up, with no visible exhaust, no plume, no thermal signature, nothing to indicate propulsion of any kind. Its surface reflected sunlight. Strangely, its shape was unclear. Its motion was oddly stable. Scientists proposed explanations, from exotic ices to unusual outgassing to fractal structures made by natural processes unknown to us. But none of them fit the data perfectly. Oumuamua remains a reminder that even in the familiar space of our own solar system, objects can behave in ways that defy every conventional model. Yet Oumuamua is only a small-scale anomaly. On cosmic scales, there are flows of matter whose speeds are far more unsettling. One such example is the phenomenon known as the dark flow, a massive directional motion of galaxy clusters across the sky, clusters that should be moving, randomly pulled by local gravity, instead appear to drift in the same direction, as if responding to an enormous gravitational influence beyond the observable universe. Some of these structures move at hundreds or even 1,000 kilometers per second toward a region of space we cannot see, cannot measure, and cannot access. The existence of such flows suggests possibilities that challenge our understanding of the cosmic landscape. Perhaps a colossal structure beyond the visible horizon is pulling entire regions of space. Perhaps the early universe contained variations in density or curvature that still echo today. Or perhaps the flows are relics of pre-inflationary physics, the faint fingerprints of a universe older than the universe we know. The puzzle grows deeper when we examine the apparent motion of distant quasars, these brilliant cores of ancient galaxies emit jets of energy, so intense, so focused, that they appear to move faster than light. Of course, nothing can truly exceed the speed of light, but when matter is propelled to near relativistic velocities, and the jet is pointed almost directly toward us, a visual illusion occurs. The light emitted at different moments reaches us in such a way that the motion appears superluminal. It is not a violation of physics, but a consequence of perspective at extreme speeds. Still, the effect is so striking that early astronomers struggled to accept. that the universe could generate such power, such acceleration, such focused beams of energy and matter. But even quasars do not represent the final boundary of unexplained motion in deep cosmic collisions. When galaxies merge, their stars pass through one another, mostly unaffected. Their gas clouds interact, heat up, compress, and ignite star formation. But their dark matter halos are expected to slow down, mutually dragging against each other through gravitational interaction. Yet in some collisions, astronomers observed something extraordinary. The ordinary matter collided and slowed. The galaxy's gas was shocked and compressed. But the dark matter kept moving, behaved as if it barely interacted with anything. It slid forward without hesitation, without friction, without delay. This behavior, dark matter passing through, as if unimpeded, suggests that its properties may be even stranger than previously believed. Perhaps dark matter collides with itself far less frequently than expected. Perhaps it exists in multiple states, some more interactive, some nearly transparent. Or perhaps what we call dark matter is a collection of several different components, each obeying rules we have yet to uncover. These high-velocity anomalies, from stars to interstellar objects to cosmic flows and dark matter halos, suggest a single conclusion. The universe is still hiding mechanisms capable of accelerating matter in ways we barely comprehend. And the patterns we observe may be fragments of a larger structure, a deeper physical system, stretching across dimensions and epochs far beyond human reach. Hypervelocity stars are rare, enigmatic, and profoundly unsettling reminders that the calmness of the night sky is an illusion, but they are only one piece of a much larger, much stranger picture, because scattered across the universe, we find objects and entire structures moving too fast, far faster than any known mechanism should allow, as if responding to rules we haven't yet uncovered. We now turn to another mystery, one that passed through our solar system quietly, briefly, but left behind questions that continue to disturb scientists today. In late 2017, a telescope in Hawaii detected a faint, elongated object moving in a trajectory unlike anything ever seen before. At first, astronomers assumed it was a comet, then an asteroid, then something in between, but nothing quite fit Oumuamua, whose name means a messenger from afar arriving first, was small, featureless, with no visible coma, no dust trail, no jets of gas. Yet, after passing the sun, it accelerated very slightly, but undeniably. And here is the problem. A comet can accelerate if it vents gas or ice, but Oumuamua showed no signs of venting, nothing detectable, nothing measurable. It behaved like an object that should not be able to behave this way. Some scientists proposed that it was made of exotic ices that evaporate invisibly. Others suggested an extremely thin, pancake-like structure pushed by sunlight, like a solar sail. A few even wondered if it was artificial, a fragment, a shard, or debris from a civilization long extinguished, not because it looked artificial, but because the acceleration was so difficult to explain within known physics. Whatever it was, its visit was brief. It entered our solar system, accelerated, and disappeared into the dark. A messenger that delivered no message. A question without an answer, on scales larger than galaxies, larger than clusters, larger than superclusters. Astronomers discovered something that strained imagination. Entire regions of the universe, containing trillions of stars, thousands of galaxies, and unimaginable quantities of dark matter, appear to be drifting in a single direction, a coherent motion, a vast, mysterious, cosmic migration. This phenomenon is called a relic flow. Sometimes it is referred to as dark flow. And here is the mystery. The motion is too large, too fast, and too organized to be explained by gravity. From any known structure, it's as if something beyond our observable universe, something enormous, something powerful, is tugging on space-time itself, pulling entire galaxy clusters like leaves caught in a current. Some theories suggest that this flow is a leftover imprint from the early universe, a relic from a time when matter was not yet settled. Others propose that something outside our cosmic horizon, perhaps a massive region of overdensity, or even another universe, is exerting gravitational influence. We cannot see the cause. We cannot measure it directly. We can only observe the motion and accept that something is moving the cosmos in ways that defy our models. There are objects so distant that their light began traveling toward us billions of years before Earth existed. Quasars, the blazing hearts of young galaxies, powered by supermassive black holes, feeding at furious rates. Some quasars, when observed, appear to be moving sideways across the sky at speeds faster than light. Of course, nothing can truly exceed the speed limit of the universe, but the illusion comes from relativity itself. Jets of plasma launched from the poles of a feeding black hole move incredibly close to the speed of light when the jet is pointed almost directly toward us. The combination of its velocity, the finite speed of light, creates an effect called relativistic superluminal motion. To our telescopes, the jet seems to move faster than light, but this illusion reveals something deeper. These jets contain unimaginable energy, launched from environments where space and time warp, where matter and magnetism twist into forms we barely understand. They are not merely fast, they are demonstrations of the extreme limits of physics itself. When galaxies collide, stars rarely hit each other. Space is simply too vast, but their gas clouds interact, crashing, compressing, forming new stars in brilliant bursts. Yet, when astronomers observed the famous bullet cluster, they witnessed something profound. Two galaxy clusters collided at tremendous speed. The visible matter, gas and dust, slammed together and slowed down. But the dark matter passed straight through, barely affected. No slowing, no friction, no resistance. It moved as if the collision had not happened at all. Dark matter, the invisible framework that shapes the universe, behaved like a ghost. Its refusal to slow down provided one of the strongest proofs that dark matter is real, that it obeys rules unlike anything we understand. It flows through collisions, through galaxies, through us, unaffected, undisturbed, silent, hypervelocity stars, interstellar visitors, intergalactic flows, relativistic illusions, ghost-like dark matter. Each phenomenon seems separate, unconnected, strange in its own way, but together they reveal something profound. The universe is not slow, static, not stable, but dynamic, restless, and filled with hidden currents. Much of this motion we barely perceive. Much of it we do not understand. Yet all of it points to the same conclusion. There are forces at work, structures unseen, rules not yet discovered, shaping the behavior of cosmic objects on every scale. Sometimes these forces create motions that seem impossible, but the impossibility is only a sign that our understanding is still incomplete. When we look upward, we see calmness, stillness, a quiet dome pierced by points of light. But in reality, those points are racing, spinning, colliding, escaping, falling, and accelerating through a universe far more violent and far more beautiful than our senses can tell. The night sky hides its motion behind distance and behind time. But if we could see the true speeds, the true flows, the true currents, oh, the cosmos, we would understand that the universe is not a place of quiet. It is a place of motion, driven by forces we are only beginning to glimpse. And somewhere out there, beyond our horizon, beyond our understanding, might lie the answers to why some objects move too fast and why the universe still holds so many secrets, waiting to be discovered. The universe hums with signals we cannot explain, pulses of energy, flashes of light, radiation arriving from the void. Without any visible origin, some bursts appear only once, brief, like a cosmic heartbeat, fading into darkness. Others repeat over months, years, their rhythm consistent, yet the source remains hidden. Among the most mysterious are the repeating fast radio bursts. First discovered in the late 20th century, arrive as brief radio pulses, lasting milliseconds, but releasing as much energy as the sun emits in a whole day. Some FRBs repeat, their signals arriving at precise intervals, suggesting a mechanism, or perhaps an object, yet no visible star, no pulsar, no galaxy can be conclusively linked. The theories are many: neutron stars, magnetars, colliding stellar remnants, even speculative ideas of artificial origin, but none explains all observed phenomena, especially those bursts that recur with regularity over months or years. Another category are the mysterious radio beacons, signals, sometimes periodic, coming from deep space without any detectable object. No star, no nebula, no accretion disk, nothing to account for the energy. Astronomers monitor them, count the pulses, measure the frequency, attempt to triangulate, but always the source remains invisible. Then there are the anomalous X-ray missions. Galactic centers, often calm, suddenly emit X-rays without an active nucleus or accretion phenomenon to explain the brightness. The intensity fluctuates, sometimes over hours, sometimes over days, yet no material structure can be observed to produce it. Some theorize strange stellar remnants or interactions between dark matter and normal matter, but the truth eludes us. Adding to the mystery are the dark gamma-ray bursts. Light is detected, brief, spectacular, but the source remains unseen. No galaxy, no afterglow, no host object. The bursts flash, fade, and leave behind only questions, like ghosts etching signatures into detectors, but refusing to reveal themselves. And of course, there are strange pulsations that defy categorization. The famous wow signal is one of the earliest examples. A strong, narrowband radio signal detected in 1977, lasting 72 seconds, never repeated. The signal, brief, intense, arrived from the Sagittarius constellation with a frequency close to the hydrogen line. A curious fact, considering hydrogen is the most abundant element in the universe. No natural source, star, nebula, or pulsar fits the observation. No technological explanation from Earth could account for it. Astronomers debated, checked every possibility, but the origin remains unknown. The signal seems like a whisper from a distant corner of the cosmos. Perhaps a message, perhaps a natural anomaly beyond our comprehension. Modern instruments have found hundreds of similar bursts. Since then, some repeating, some one-off, some aligned with known galaxies, others floating in apparent emptiness. Yet, each detection challenges our understanding and deepens the sense that the universe is alive, sending pulses, signals from unseen corners beyond direct observation, and perhaps beyond current physics. Every pulse recorded, every flash measured, every unexplained X-ray or gamma signal is a testament to the cosmic complexity, to the fact that the universe contains phenomena we are only beginning to glimpse. Some physicists suggest that these signals may involve unknown particles, dark matter interactions, or unknown fields of energy permeating space. Others speculate magnetar flares or collisions of exotic objects like quark stars or miniature black holes. Yet the truth is still beyond our reach. The universe emits, and we listen patiently, ever hoping to link the mysterious signals to known processes, to explain the unexplainable. But with every new detection, we are reminded the cosmos is far stranger than our textbooks describe, far more unpredictable, and far more alive than any calm night sky would suggest, even in the seeming silence. Hidden pulses, mysterious flashes, and anomalous radiation speak in rhythms we are only beginning to understand. They hint at structures, forces, and objects that exist beyond our current vision. They whisper of physics we have yet to uncover, and of a cosmos that constantly surprises us. The universe is not just light, not just matter, not just galaxies. It is motion, energy, information, sometimes audible to instruments tuned finely enough, sometimes fleeting, sometimes repeating, always mysterious. Yet the universe is not cruelly silent. Dew communicates in bursts, in flashes, in strange, unexpected rhythms. If only we know how to listen. Some repeating FARB, show patterns like a heartbeat or a rotating beacon. The intervals are precise, sometimes minutes, sometimes hours, sometimes days apart, but always consistent in ways that hint at a mechanism or perhaps a structure we cannot see. Astronomers have mapped these signals, tracing them across the sky. They often seem to originate from distant galaxies, billions of light years away, yet their energy, millions of times greater than our sun's output, reaches us in milliseconds, like cosmic Morse code, radio beacons, periodic signals, without a visible source, challenge the very assumption that all cosmic phenomena should have a detectable origin. No luminous object, no pulsar, no nebula corresponds to the observed pulses. They are sentinels in the void, reminders that the universe has secrets hidden in plain sight, X-ray anomalies in galactic centers further deepen the mystery. Some galaxies, calm invisible light, emit sudden bursts of X-rays from regions where no accretion disk or active nucleus exists. The missions are real, measurable, energetic, yet their cause remains unexplained. They flicker, rise, fade like invisible fireworks, lighting only the detectors. And then there are the dark gamma ray bursts, explosions of energy detected in gamma ray observatories, with no associated source in any wavelength. Light exists, but its progenitor does not. It is as if the universe is speaking in riddles, showing only the effect and not the cause. The famous wow signal serves as a reminder that the unexpected has always been with us. A narrowband signal, brief, detected from the constellation Sagittarius, peaked and then vanished, never repeated, yet forever etched into the record of human observation. Some scientists speculate that these signals are natural, that they are generated by mechanisms yet unknown, magnetars, exotic compact objects, or interactions with dark matter. Though entertain the possibility of technological origin, but without repeating confirmation, nothing can be proven. Modern arrays, like Chime and Fast, have detected hundreds of FAFRBs, many repeating, many isolated, some coming from known galaxies, others seemingly from empty space. Patterns emerge, yet explanations remain elusive. Perhaps these bursts are clues to the invisible structure of the cosmos. Perhaps dark matter or unknown energy fields are colliding, creating flashes of radiation we can only detect indirectly. Perhaps entire processes, operating at scales far larger than galaxies, produce energy in ways we cannot yet model. The energy released in a single 4B can be comparable to the sun's total output in days or even weeks, compressed into milliseconds. It is a scale so extreme that it strains imagination. We struggle to comprehend how the universe can generate such power and hide its source simultaneously. Even with gamma-ray bursts, X-ray flares, and anomalous radio signals, we see only shadows of their mechanisms. The objects themselves remain hidden, the physics uncertain, the origin mysterious. The universe, in this respect, is a storyteller, with parts of the tale concealed. We perceive the effects, the whispers, the flickers, but the actors remain cloaked. These signals, these unexplained emissions, teach us humility. They remind us that the cosmos is more complex than our models, than our instruments, than even our imagination. They hint at structures, hidden energies, known interactions, and processes beyond known physics. And so we listen, carefully, attentively, charting pulses, bursts, and flashes, hoping to one day connect the dots and uncover the mechanisms behind the mysterious cosmic voices, the universe, through farbs, radio beacons, X-rays, dark gamma bursts, and fleeting signals like the wow signal is speaking in a language we are only beginning to understand. And each D10 brings us one step closer to translating the whispers from the hidden depths of space to knowledge. And in these unexplained emissions, we find not chaos, but order waiting to be discovered, patterns in the void, messages in the darkness, and a profound reminder that the cosmos is alive, with energy, motion, and mystery far beyond our current comprehension. The universe is not only filled with stars, galaxies, and clouds of gas, but perhaps with hidden threads, thin, dense, and potentially destructive threads that defy imagination. These are the cosmic strings, or as some theorists call them, destruction strings. They are hypothetical, so small, so thin, that their width could be less than an atom, yet their density, their mass, could exceed anything found in ordinary matter. Imagine a line threaded through space, born in the first fractions of a second after the Big Bang, carrying with it energy, compressed to extremes that boggle the mind. Some models suggest that cosmic strings formed from phase transitions in the early universe as the universe cooled and fundamental symmetries broke, like cracks in ice or flaws in a crystal. These quantum defects could stretch across vast distances, potentially spanning galaxies, even clusters, without ever being seen. They are not luminous. They do not reflect light. They barely interact with ordinary matter, invisible threads floating in the cosmic fabric. Yet their presence, if confirmed, could explain phenomena we currently struggle to understand. For example, the early universe was a seething, turbulent plasma, expanding and cooling, while cosmic strings could act as gravitational lenses, warping light from distant objects in subtle, nearly undetectable ways. They might pull matter along them, creating lines of galaxies, filaments, and voids, shaping the large-scale structure of the cosmos. Despite their small width, the energy they carry could be enormous. A single centimeter of a cosmic string might contain more mass energy than a mountain or even a planet. Some theorists suggest that if one of these strings moved through a galaxy, its gravity could accelerate stars, disrupt planetary systems, or even trigger bursts of radiation as matter interacts with the extreme field. Yet, detecting them is nearly impossible. They leave no light, no sound, no heat. They are shadows in the vacuum, defects in space-time itself. Some models propose that these strings are connected to higher dimensional physics, to fields and forces beyond the standard model, that their effects could appear only under extreme conditions. For instance, when two strings intersect, they might produce a cusp, an event releasing energy so intense it could rival the output of a supernova in an instant. Or they might oscillate, radiating gravitational waves, ripples in space-time, that current and future detectors might someday capture. Some cosmologists have speculated that cosmic strings could also leave imprints in the cosmic microwave background, tiny anomalies in temperature and polarization, tracing lines of energy from the earliest moments of the universe. Their invisibility and the subtlety of their effects make them both elusive and tantalizing. We know they are possible within the equations, but finding direct evidence remains a monumental challenge. The threads could, like hidden fingers of the cosmos, stretch across millions of light years, connecting massive clusters in invisible lines, hints of a structure we cannot see, yet that shapes everything. Even their origin is a mystery, some suggest. They formed as a result of symmetry violations. Others propose that they are relics of topological defects from the first moments after the Big Bang. Their density, their tension is so extreme that if one passed near a star system, the gravitational effects could be catastrophic, pulling planets from orbit, accelerating matter, and creating energy bursts that might be detected across the cosmos. Yet, because they are narrow and interact weakly, most pass unnoticed. They might crisscross our galaxy. We would never know. Some theorists even speculate that cosmic strings could explain some of the most energetic phenomena observed: fast radio bursts, gamma ray flashes, or ultra high energy cosmic rays, tiny hints perhaps caused by encounters with these hidden threads. And so the picture emerges of a universe not only alive with stars and galaxies, but threaded with invisible filaments, remnants of the earliest cosmic moments, strings of energy compressing space-time itself, potentially capable of destruction, yet mostly undetectable. Cosmic strings, if they exist, are relics of the earliest universe, born in the first fractions of a second, when temperatures were unimaginable and energies far beyond our current reach. They carry the story of creation in their tension and in their invisible paths. These threads, slender as an atom, yet denser than anything, could stretch across millions of light years, connecting the universe in lines of hidden energy. Some theorists imagine that cosmic strings are not isolated. They could form networks, intersecting, knitting the cosmic web together in ways we cannot yet perceive. At intersections, the energy could concentrate, producing bursts of gravitational waves, ripples that propagate across the fabric of space-time, signaling their presence in subtle distortions of the universe. Despite their power, they are mostly invisible. They do not emit light. They do not absorb light. They barely interact with ordinary matter. Their existence can only be inferred through gravity or through the traces they leave on the largest scales or the tiniest perturbations. Some models suggest that cosmic strings could even bend space-time in ways similar to black holes, but without forming singularities, creating invisible corridors through which matter and energy might accelerate to unimaginable speeds. If one were to pass near a star system, the effects could be catastrophic. Planets could be displaced, stellar orbits distorted, and enormous energy released through the interaction of normal matter with the concentrated tension. Oh, the string? Some theorists speculate that encounters with cosmic strings could produce the most energetic events observed. Fast radio bursts, gamma-ray flashes, high-energy cosmic rays, all hints of these elusive threads interacting with the matter we can see. Yet, the paradox remains. Their incredible density, their potential energy, and their near-total invisibility. They are the ultimate ghost structures, the invisible skeleton of the universe, stretching through space, holding secrets from the very birth of existence. These strings may also hold clues to the unification of forces and the nature of fundamental physics. Some ideas suggest that they arise from the breaking of symmetry in the laws governing the early universe, where the forces we know today were once unified, and space-time itself had different properties. Through these defects, we may glimpse the mechanics of creation, the structure of the vacuum, and the extreme energy scales we can only theorize about. They remind us that the universe is not static, not fully observable, not confined to what we can detect. There are relics, hidden threads, cosmic scars, carrying energy and information from the earliest moments, beyond our instruments, beyond ordinary matter, beyond light itself. Cosmic strings like invisible rivers of energy, may crisscross the cosmos, connecting galaxies, clusters, and voids, shaping large-scale structure, pulling matter along unseen lines, and leaving subtle imprints in gravitational waves, lensing, and radiation. Even if we never see them, their existence could explain some of the most mysterious phenomena in the cosmos. They may hold answers to questions we have not yet formulated, and mysteries we are only beginning to perceive. And so, the universe does not reveal all at once. It hides threads woven into the fabric of space, threads capable of destruction, threads born from the most extreme conditions, threads that may carry us to the understanding of the earliest cosmic events and the hidden architecture of reality itself. In the end, cosmic strings, destruction threads, remain one of the most fascinating and elusive concepts in astrophysics. Invisible, yet powerful. Hypothetical, yet potentially real. A reminder that the cosmos is stranger, larger, and more mysterious than we can imagine. The search continues through gravitational wave detectors, through precise cosmological measurements, through careful mapping of large-scale structure, listening for the subtle hints of energy, of tension, of motion left behind by threads that have traversed the universe since the dawn of time. And as we explore, we are reminded that even the smallest, the thinnest, and the most elusive structures can hold the keys to understanding the cosmos in its entirety. The universe is threaded with secrets, and among the most extraordinary are these cosmic strings, remnants of creation, potentially destructive, yet profoundly enlightening, waiting for the day when humanity can finally detect and understand the invisible lines that shape everything